Okay, so welcome everyone to the 2024 Vietnam seminar. My name is Arelis Guerrero, and I'm an applications manager at Texas Instruments, supporting battery management systems. I'm gonna be presenting in English, but if you need any help translating, Kian can help me out. Okay. So let's start with BMS at TI. So battery management systems, we have a great variety of product that we need, and TI has a little bit of everything to create a full solutions. So we go all the way from high precision, high efficiency battery chargers. We have super accurate base of the or gauging algorithm, as well as battery monitoring app protector for your battery system. I'm on the battery monitor and protecting, so I'm gonna be focusing my presentation on that area. So a quick overview for the agenda for today. We're gonna be covering high cell system. So we're gonna go a little bit about what's a protector, what's a monitor, and what's a gauge. We're gonna talk about protection basics, some system considerations, and we're gonna get a few examples of different systems that are considered multi-cell solutions. So the first thing to consider when you're talking about BMS systems is your battery chemistry. There are multiple types of battery chemistry. So here we're seeing the most common one used, going all the way from lead acid that used to be the top one, but still pretty popular among some automotive applications, to some nickel-based like nickel cation, nickel metal hydrate, and what we consider lithium-ion, lithium-based battery chemistry that are used in most portable applications nowadays because of their high density. And one of the things to look into when we look at lithium-ion, it has a high density, so you can store more capacity, but also you have to be really taking considerations on the protection. So protections for lithium-ion batteries are required for functional safety, and they also tend to be pretty prone for thermal runaway. So they cannot be overcharged and they cannot be exposed to extreme temperature. So it is really important on your BMS system that you protect your battery. So when we talk about high cell count systems, anything that's more than one cell is considered multi-cell. So here you can see different applications that go from 2 to 4S, like drones, to power tools, anything from 16 to 20S. Electric vehicles or 2 3-wheelers, we see anything from 48 volts to 70 volt solutions, all the way up to automotive, which we have 100 volts to 400 volt solutions, and energy storage system, which can go to 1,000 volts and 1,500 volts on utility scale. So there is multiple type of applications that use multi-cell solutions, and the way to design for them will depend on your application type and the requirements for functional safety. We're gonna cover a little bit of all of them all and kind of the system consideration you have to take for each one of them. So the first topic is what is a protector, a monitor, and a gauge. So when you are looking into how to protect your system, you have multiple options about the requirements, and it can go all the way for the lowest complexity to the highest integration. So at the more basic level, we have protectors. So protectors are mostly basic protection for your battery. They are typically used on comparator-based solutions, and they can be paired with a monitor for redundancy. When we go a step up, we have what we call a monitor. So a monitor will include all the protection system, but it will also monitor the battery. So you will have an integrated ADC. They typically would also include cell balancing and can be used as standalone solutions, or it can be programmable with the MCU. The monitor gives you the more flexibility, as you can pair the monitor with an MCU and create your own gauging algorithm. If you're looking for the best integration and you're looking for SOH, SOC report, you will need to consider a gauge. So a gauge includes the protector, the monitoring, but also the algorithm to calculate the SOC and SOH. So this is the more complex of them all, but doesn't give you the flexibility that a battery monitor can give for your system. So there are multiple solutions, and some of them can be used in combination with each other in order to protect your system, and it will heavily depend on the applications you're using. So when we are looking at battery packs and the key considerations we have to take, we can look into anything from functional safety is especially critical when we consider lithium-ion type of chemistry. We also trying to look into that voltage, current, temperature measurement and that high accuracy that you can use to calculate your state of health, state of charge, so you can get the most out of your battery pack. Another important consideration that is key for multi-cell system is cell balancing. When you have a single cell, you don't have to balance, but when you're looking about more than 2 cells, you wanna make sure that you do have cell balancing into your system. Having reliable communication is critical. All of this BMS will be paired with an MCU. It could be a C2000, it could be an MSPN0. And you need to be able to have a reliable communication so your system can take action as needed. And finally, a key consideration for corporations and companies is how much can you scale the hardware and the software across solutions. So given the flexibility in those tools to grow your system as time passes is pretty critical. So let's look a little bit closer into some of the challenges for high cell count system. One of the key things is the safety standard. Safety standard will vary depending on the applications you are using. And here I'm highlighting a few of the most commonly used safety standard for battery, but this could vary by region, by your application. So it is important if you're working a system that's lithium-based to work with your safety certification company to get the details into what do you have to do to make sure you meet their safety standard at your system level. Another thing to consider is cell balancing. Multi-cell system, we have to look into cell balancing. If we have an advanced battery pack that needs something bigger than a protection system, you also have to work with the implementation or the monitor or the gauging into your software and firmware. How to design your system using high or low side fed, as well as what solution are you going to use to calculate your gauging. If you go to a integrated gauge solution, you have impedance track, which is the TI proprietary gauging algorithm. And if you use a monitor, you will do that on the MCU on your own, so you have the flexibility of the monitors. And another important consideration, some of the monitors we have and protector, they go, let's say, up to 20S. So if you're working in a system that goes to extremely high voltage, such an automotive or ESS system that goes all the way to 1,000 volts to 1,500 volts, you need to be able to stack them together. So how to consider stacking your solution to create those high voltage signals are also pretty critical. So I'm going to go over a little bit more in details in some of the basics terminology, as well as the system considerations that you need to consider when you're designing a BMS solution. So the first thing to look into protections will be voltage. As I mentioned, lithium-ion based technologies are pretty prone to overvoltage. So overvoltage is the key protections that is required by every single safety standard, and all your systems should have an overvoltage protection. So the way the protector, the monitor works, it has a comparator inside, and the moment the voltage exceeds that, it will take actions to open that FET and disconnect the battery from the system to avoid the battery getting damaged and your system suffering from the same. When we talk about primary versus secondary protectors, we're looking into permanent failure versus a recoverable failure. So if we look into primary protection, we can have a fault, like an overvoltage. We open the FET, and the moment the fault goes away, we reconnect the system continue operating. When we're looking into secondary protection, we're looking into a permanent fail mode. So if your primary protection fails, you need to make sure the safety of your system is guaranteed. So some safety standard will require you to have a permanent fail or secondary protector on your system. Typically, secondary protections will blow a fuse in your system, so at that point, the battery patch will be scrapped. Having that redundancy allows you for, if it's a temporary fail mode, you can protect your battery, and the moment the failure is permanent, you make sure no further damage happen. So this is showing exactly like how that overvoltage protection works. And again, if it's a primary failure, it will open the FET. The FET could be high side or low side. But if it's a permanent fail, it will blow a fuse and pretty much your system will be not usable anymore till that battery gets replaced. Under voltage is similar to overvoltage. A lot of people understand that lithium-ion over voltage can damage the battery, but also going extremely under voltage can damage the battery. So it is important to also protect your battery for going too low. If your battery consistently goes extremely depleted, it will reduce the capacity of the battery, but it could also create a short system in your internal battery due to the chemistry. So some of the secondary protector, and it's not as critical as over voltage, will be to also look for under voltage on your lithium-ion battery. The mode of operation is the exact same as the over voltage, but on the opposite direction. Another key considerations for protection will be current protection. Current are typically done in your system as a current shunt operation. So you will have a sense resistor that's going to be monitoring the system load of your system, either on charging or discharging, and it will take the appropriate actions to protect the system for going too hot and creating some thermal runaway. Protections are common part of some monitors or could be implemented externally on your protectors as well. And last but not least is temperature. So temperature protections is done on monitors and protector, typically using an NTC solution. So we have thermistors in the monitor that are going to be consistently sampling that voltage, which is an equivalent of your system temperature, and we'll be taking actions to make sure your battery doesn't exceed the threshold. So if you are familiar with JEDA, when you're charging a battery, you have to make some considerations at cold and hot temperature. So this will prevent that from happening. And lithium-based technologies are pretty susceptible to temperature changes and can get damaged if it exceeds a certain hot temperatures. So we want to make sure if your environment is, let's say, extremely hot, the battery gets disconnected till it is safe to continue operating or resume charging. So let's look more into, now that we understand all the protections the key protections we have to consider on our system, let's look into some of the system considerations we have to take. The initial one is, where do I put my FETs? And this is a common questions we see when people are starting working with battery management system. Having a high side connection versus a low side connection, and there is not a right answer, but more like different options that you can consider. And we do have protections for both low side and high side FET. If we look into the low side FET, this is going to be the lowest cost and complexity. But because of that FET connection is on the ground side of the system, it's going to disconnect your system in case of a failure. So if you get, for example, an overvoltage failure, this will open, and then your MCU is not able to talk to the device anymore. So you will need some type of isolations here if you want to use this, and you have the low side FET needed, and it's integrated on the BQ76900 family. If you prefer, one of the key considerations for low side, if you're working on a really high voltage application, such as automotive or ESS, and you're talking about 1,000 volts, you cannot implement high side FET. So in those kind of isolated array system, low side FET is a great solution for you to be able to protect your battery and still have that isolation communication. If you are working on an applications and you prefer high side FET, the advantages is because the FETs are not on the high side, you're not going to lose your ground connection. So you're going to have that constant communication regardless of the protection being open. The high side FET, it is more complex, and it will require to have a charge pump to be able to open those high side FET. On the BQ769X2, we have those FETs integrated drivers, so it's easier to implement. And this is typically used on applications that are 48 volts or less. So one of the key points when we're talking about multi-cell systems, you have more than one cell and they are not identical. So due to degradation, manufacturing differences, they will not age the same way, they will not be the same way. And when you're looking at your battery life and you're doing your gauging algorithm to calculate your SOC and SOH, you want to be able to keep them as consistent as possible through their life so you can get the more of your battery pack. So this is when we start looking into cell balancing applications. How can we make sure if I have 3 cells in my system that they are equally aging at the same rate and that I'm getting the most out of them? If I have a battery on my 3-cell system that's slightly overcharged, when I'm charging my battery and that battery gets to the threshold, my other 2 cells will not charge all the way as needed. And this is the same on the opposite direction. If I'm discharging a battery and one of them is extremely depleted, then I have capacity that I'm not using. So having them equally will mean I will be able to use my system the longest time and get the most out of my battery life. So in order to achieve this, you have to consider cell balancing. Most of our monitors and gauges will include some passive cell balancing system. So how does that work? If you have a If you have an internal FET inside the multi-cell solutions, and one of them needs to be balanced to the other, we're going to use a passive system. We're trying to deplete the excess energy in that cell so it matches the lowest cell in the system. So let's say on my 3-cell system, one of them is slightly over. We're going to activate that internal FET so that the current start flowing through that balancing resistor and it start depleting the energy so we can lower that cell to match the other two. And we will continue doing this at set intervals that you can configure on your system so that the battery stays at the same level. As this resistor will determine the current of that cell balancing, you have some limitations on how much can you balance. And the higher the current you have for balancing, the quicker that cell will get depleted, so the quicker that balancing will happen. So in order to increase that current and in the same time increase the time it takes for balance, you might consider something such as external cell balancing. So the idea or operation on this is that we are going to add external FETs to our system, and we're going to use the internal FET to activate that external FET. So we have a higher current that can flow through the system, therefore it can deplete your battery quicker. So here you can see, the cell is ready to serve balance. This is going to activate the internal FET. That's going to activate that external FET, and it's going to have that increased current that's going to equalize that cell quicker to the others. And another consideration is, when do we use a monitor and when do we use a gauge? As I mentioned before, monitors give the biggest flexibility as you're pairing your monitoring system with an MCU, and you can do your gauging algorithm. Gauges are more integrated. Also, monitors can be paired with a gauge, like a top-of-stack gauge, to get that gauging algorithm from you. So the decision into when to use more, when you're trying to get all the cell voltages in your system as well as the balancing, and you are okay with the level of algorithms that you have on your system, it's the most cost-effective solution, a monitor could be the perfect fit. And if you only care about gauging on the top of stack, it can be paired with a gauge. If you're looking for a more precision integrated solution when you don't want to have the control of the gauging yourself, then you can look into some of the integrated gauging. The cost will be significantly higher, but you do not have to create the algorithm on your system, but you lack the flexibility of control. So whatever is on their system, that's what it will be as it's integrated. So we do have multiple solutions, and it really depends on your needs and how accurate your system can be. One of the things about gauging, they do include a black box feature. So if in case of failure, you can recover that like planes and see what happened on your system. You can also implement this on your own applications with a monitor, but it's a common integration on gauges. So functional safety is a key topic for battery management system. If you're looking at lithium-ion, there will be some functional safety requirement in your applications, and they will vary, as I showed before. There's different UL CE certification. One of the important things to mention is that functional safety is a system level protection, It's not as specific to the monitor gauge IC, but more about all your components and your applications. So the different ICs will have the necessary features to help you pass the certification, but you need to understand what sort of additional circuitry you need to add. A common example is some certification requires for fault redundancy in some of your system. So your monitor could include a fault redundant in this ADC integrated, or you might need to pair that monitor with a secondary protector or with an additional ADC in order to meet that system level requirement. So understanding your applications and your system requirement to pass certification is important, and obviously we can help you kind of pick the right solution based on your industry. So when we're looking into high voltage system, when we're looking into applications that need to be stacked to a voltage higher than 50 volts, for example, we have to consider how are we going to design our system. And there is 3 key architectures we see on high voltage solutions, such as automotive or ESS. The first one is the centralized. So when we look at the centralized system, what we have is all the cells are externally, and we have all the monitors set together in a system connected to the different cells. So if you have 100 cells, you have your 100 cells connected in series, and then all the monitors in a single PCB board that will be connected to those cells. Another common architecture is what we call distributed system. So on distributed system, let's say you have a 16S monitor, you will connect your 16 cells with your monitor, and that will be your module, and then you're gonna stack the modules instead of stacking the cells together, all the way to your high voltage solution. Most commonly, we see a mix or combination of these two due to mechanical reasons. If you're looking into high voltage applications, if you're looking to an automotive or an electric vehicle, you have to consider the mechanics and the space. And if you look at ESS, you have to consider how are you going to be assembling those cells. So having a combination of those two systems, or one versus the other, is pretty common. But understanding how your system is going to be designed is important to choose the right solution. So if you're looking into stacking systems for high voltage system, there are multiple options you can consider. Here is 2 key examples of different configurations that you can use. So we have the BQ769X2, which is a family that can go to 16S. So you can stack that into 2 devices externally together to achieve 32S in your system. This is a common configuration for things like E2W solutions when we're trying to get that 48-volt application. Another option is to go to one of our stackable monitors. Stackable monitors includes a daisy chain configuration, so it allows you to more easily stack devices, and this can go all the way to 100 volts to 1,000 volts. So this is more commonly used for applications and systems that require that high level of a voltage, and we see it pretty commonly used in automotive or ESS solutions. A quick overview of BIF. BIF is TI proprietary daisy chain configuration. So all of the devices can be communicating together through this daisy chain. Is fully integrated. You do not need to add any additional code to your system, and it allows the different monitor on that stack solutions to communicate and transfer data among each other. In applications where the distance of those high voltage systems can get really long. It is really important to have that reliable communication and make sure you're not going to lose that track all the way to the high voltage system. They could also allow the system to be connected in a ring configuration, so you have that flexibility. If something happened with a wire, you can still talk to your stack. So when you're looking into, I have that daisy chain communication, and I have 20, 40 different boards connected talking to each other. How do I make sure I have the right type of isolation? How do I make sure I'm not going to be connecting my 1,000 volts to my ground and creating a short? So selecting the type of isolation is important, and we support everything from a capacitive-only isolation to cap choke to a transformer isolation. There is pros and cons. Normally, we recommend capacitor isolation to be only on the same PCB. Cap and choke is a good in-between solution to be a little bit more robust. And if you're looking into distance, the best will be to consider transformer isolation, but that will also come with the price point. So we do have a lot of different designs already and recommendations for your transformer, as well as your passive component, to make sure you can safely use or daisy chain and keep the communication reliable and robust. Okay, so I'm gonna be going about a few examples and options. We do have a really big portfolio that can fit most applications, but I'm gonna give some recommendations for 3 of the most common systems we see in multi-cell solutions, and a possible pairing for a monitor that could work in your system. So one of the first key things we see is 12 volts in automotive systems. So we see it as part of a lot of the auxiliary voltages we have nowadays in our really smart cars, and we need to create kind of that small voltage solution in our system. So here you can see a quick overview of where that 12-volt solutions will be in your EV. So for those type of applications, we need something up to 7S. So we have the BQ76907, and this is a quick overview of the different functionalities that device have. It has a low side FET driver. It has integrated cooling, cell balancing, thermistor, column counter, LDO, so it's highly integrated and really good for those low to medium cell count all the way to 7S solutions. If you're looking for a quick reference design up to 7S in your system, we do have this TIDA 010260A. It's designed with our appliances thing, and is mostly targeted for power tool, but it could be applicable for any up to 7S solution. So I will say if you have a system that works in that area, take a look at this one, and it has everything that you need to get started. If we're looking a little bit more higher voltage, let's say something like a 48-volt automotive, or something like a e-mobility, like two-wheelers, three-wheelers, we're looking something in the 48 to 72 volts. So 7S will not cut it, so you need something more like 16S to 20S solution. So we do know we're seeing the movement in being here for 3 days, and I know the amount of two-wheelers and three-wheelers we have here, as well as different EV. So this is definitely a key applications for most actually countries in Asia, and having a good reliable solution that can still meet your safety requirements is really important. So for those type of applications, the best My recommendation will be to look in the BQ769X2. It has the 52, which is a 16L, as well as the 42, which is a 10S solution. It has two independent ADC, so it will provide your voltage as well as your current measurement. It has high side FET drivers, so you will not lose the communications in your system in case of a fail. We do have different applications design of how to stack two of the solutions. So if you're looking into a 48-volt system, one single AFE will do. If you're looking into 72, you can stack two of them together to get to that voltage. It has a really wide protection feature. So have every single type of protection. We cover voltage, current, temperature. It also has a secondary fuse. So it integrates the primary and the secondary protections in the same chip. It can work as a standalone solution without any MCU, or it can also be configurable through your MCU to change those parameters as needed. It does have autonomous and also host control cell balancing, so the device itself can do all the cell balancing for you, or you can have the flexibility to set it to your desired settings. And one key important thing to mention on this one is can be programmed the OTP on your system, so you can get this device, set it to your desired protection, burn it on your customer production line, and have it going without having to wait for a new spin from TI. So it's a pretty powerful device, and it has a lot of different options for most applications that are in this 10S to 32S system. Again, we have multiple different TI designs with all of our monitors in different applications with a collaboration with the same team. In particular, this one is a 10S to 16X reference design, and it uses high side FET. So you can get this one online, and you can see the full schematic drawing on how to set up the system in a high side configuration. Okay, and finally, we have to consider, what if I need more than 48 volts? What if I need to go higher? With the electrifications we see, we mentioned two-wheelers, three-wheelers, but we also have EV. And we're also trying to be more health, environment conscious, right? So we're having a lot of ESS movement. So this is a quick example of BMS on your home. How does it look? So you have the utility, and utility in the grid scale is collecting all of this energy and is storing this on ESS all the way to 1500 volts. So we're talking about 400 different cells that has to be monitoring that solutions. And then we have residential or commercial, if it's a bigger building, ESS on your home. You might have a power wall when you are using and harvesting that energy from the sun as well as from the grid to power your home, and have some home automation. We also have BMS, and then you might have an EV on your system, which is another high voltage system, and EV can go to 100, 400 volts as well. So if you can consider all the different applications where BMS is, it's important to make sure you design for the safety of low voltage, but also high voltage systems. So if you have to look into high voltage, we need to go back to how do we stack them? How do we safely go from 16S all the way to 400S and still be able to communicate and still be able to provide a reliable system? So this is a quick reference design. It's using the same BQ76952, but now it's on a stackable solution. So it will go up to 32S. So this will be really good for anything in like the low voltage auto, like 48 volt automotive, up to residential ESS. So if you want to see how you can use the BQ76942 in a stack configuration, you can go to this DI design and it will show you all the schematics and the files. Another device we can consider if we're looking into something with the integrated daisy change, it will be the BQ79616. So this one will include the daisy change, so it's easier to communicate, but it will not be as integrated as the BQ76952, so it doesn't have the current shown column counter, but it can be paired with other devices to create the high voltage system. So, quick overview of what we consider high voltage architecture and how we recommend using this daisy change configuration for anything like EV or ESS is shown here. So here you can see we have the 616, which is the battery monitor, and is in this distributed architecture, so it has all the cells connected to the AFE, and it's communicating through daisy change all the way up to your top of stack. It could be 400 volts or 1,000 volts, depending on your application. So here we have what we call BCU, or battery control unit. And this is where your low voltage system lies. So you have your MCU, and you have your isolation. So you can use something like the BQ79600, which is a communication bridge to kind of transfer from the MCU UART communication to your daisy change. And you can add that into your system to keep it isolated in the low voltage. And finally, you have your high voltage system all the way on the top of your system, where we have something called battery junction box, or depending on your applications, it might be called different. But what we're looking here is how we monitor the pack. So this is where the high voltage signals are. So this is where your 400 volts system lies. And this is where we're measuring those signals to make sure everything is okay. That also includes the relay drivers to open those high voltage signal and disconnect it from the external system. One important thing is for current sensing on high voltage applications, we sense on the low side because it's a low voltage solution. So that will also include your column counter and your current shunt, and this will give all of the results, and they can be synchronized together with the TI daisy change. So you can get all those information back all the way from your high voltage signal to your MCU and do your SOC, SOH calculation for high voltage system in a pretty accurate manner. So if you're looking into how do I get started with a high voltage solution? How do I have an EB, I have an ESS, and I want to see how to use all of these devices together? I would recommend looking into this DIDA. It shows this architecture, and as you can see, is for ESS, but it's pretty similar on EB. It's a pretty similar architecture. So this will give you, again, all the schematics and all the design files you need to get starting in this type of application. And then a really cool video and a really cool applications that you might have seen on LinkedIn or YouTube is this demo about using multiple TIICs to create a EB powertrain solution. So you can take a look into the video showing all the different TI ICs used for automotive, including some of our newest battery monitors system as well. So this is how it looks, and I wish I can show you. It has a pretty cool control that you can move the car around, but it's a really good set of how do we integrate everything that we have available on the web to create a high voltage solution that's reliable. So a quick overview of some of the devices I mentioned and some of the TI design I mentioned is here. So you can take a look. I believe the presentation is online, so you can get this and take a look offline as well, and let me know if you have any questions. So to kind of summarize what we talk about, multi-cell system has different type of applications. So it will go everything from like 2S to 400 different cells, right? So the considerations and the solution will vary slightly depending on your system. But we have a lot of TI designs, a lot of solutions, and then it will show you how to create your reliable system, how to stack them together to get higher voltage and get that precision, and most of all, make sure your battery is safe and your system is reliable. As we use battery everywhere, we want to make sure we consider safety considerations first.